Welcome back. We're going to talk about something exciting, that is the maximum likelihood estimations, ML estimations. So you can see this cute confusing birds try to come up with the ultimate estimate for the data. So this will be the second lesson that we would try to learn from the data. So in previous one, we know how we can cook up an estimator to estimate, for instance, or to make a wild guess about the population means and population variance. But can we do more? So that is the whole idea. So let's move on. And MLEs. So what I'm going to do is that this is relatively intuitive, so if you have any questions, just leave it in the chat rooms and I will try to respond there in real times. So MLE or ML estimation, the maximum likelihood estimation, maximum easy, estimation easy. What exactly is likelihood? So this word was cooked up by one of the very famous statistical scientists, Fishers. So let me try to define the likely function for you here. The first step, given the sample data x1, x2 to xn, we don't really know the underlying PDF, right? We don't really know, we just know a bunch of data. And if you have doubts, you just measure more data. So you don't really have a full knowledge about the underlying probability density functions, px. So what are we going to do? Well, instead of just cooking up the good estimators to estimate the population mean, to estimate the population variance, we can be more courageous. We can adopt some hypotheses. Theories, love hypothesis, let's say this. And so in mathematical terms, that means we just choose Gaussian, exponential, Poissons, gammas, or what sort of reasonable distribution you think to approximate the problems that we face. And we think that these data were generated by the distributions in the hypothesis H. And because of that, so we have a bunch of data, right? And you assume that it follows some hypothesis, so it has these probabilities density distribution functions. And if you write it out, plugging into these x1, x2, xn values, then this will then become a function of these parameters. And these parameters are the parameters characterizing the hypothesis H. And so how can we find the best parameters for a given set of data? So what we do is the following. We just take the maximum value of this. And so basically this AI hat is the argument when the likely function reach its maximum. And if this sounds too computer science for you, that would be fine. In the explicit form, that just means that we take partial derivative of dLdAI and set it equal to 0 and solve for this AI. And this AI would be the best guess of the parameters that we start with at the very beginning. So this AI hat are the optimized estimators for the parameters AI of the PDF in the hypothesis H. Okay, so now you sort of got the logic. Let me just rephrase that one more time. Given the data set, you don't know the underlying PDF. That's okay. We just assume 1, so now you know. But this H has unknown parameters AI. So how can you figure out AI? Simple. You just take partial differentiation to see when does this likelihood functions reach its maximum. That is, this would be the set of parameters which is most likely to generate the data that you have at hand, and plug it into these optimized estimators, and then you have a full description or a full statistical model of the data. It's just this simple. So let's walk through several examples to see how this goes. And this one is really important because this is not only important in engineering, it is also important in information science. It is important and can be found in neuroscience as well. So that is basically the signal transmission in the wild. So in ancient time, you can think about if you are an operator and there are telephone coming in and coming out, and you have a switchboard operated by men, and that's why it called operators. And later on, there are switchboards. So then you would like to understand how this call comes in and come out. And nowadays, when we transmit signals through some conducting channels, you also want to have a good estimate about how dense or how efficient that the signal can be transported or transmitted through the wire. Okay, so suppose now I mark the signals at T1, T2, and T3, and the adjacent intervals, time intervals between two nearby signals is x1, x2, x3, and xn. Okay, and so these x1, x2, x3, xn's are basically random variables. So if we take n intervals of these durations and writing them as xi, suppose now that I assume that all these x are just drawn from an exponential distribution, 1 over tau exponential minus x divided by tau, where the tau is basically the mean intervals between two signals. So one can ask, what is the likelihood functions L? Remember, once you plug it into x1, x2, x3, this likelihood function is just a function of tau because I just assume a single parameter. The exponential distribution is our hypothesis. It only have one parameter tau. And let's see how good the ML estimation can give us the right answer. Okay, so let's proceed. The first step, write down the likelihood function. That is straightforward. Since the sample values are independently drawn from the same PDF, so the probability distribution function can be written as a direct product of each random variables. And this is an exponential, exponential, and exponential many times. You time them together. This is 1 over tau to the power n, and this is exponential minus 1 over tau, and the summation over all x1 to xn. Then you realize the parameter here does not really depend on each single data point, right? It only depends on the average x bar of it. So we can re-express the sum as n times x bar. So then you got a relatively simple function. This is what we call the likelihood function. Okay, this likelihood function is a function of tau. So remember, it's a little bit sick. It's 1 over tau to the power n. It's exponential minus n divided by tau x bar. And remember, as long as you have xi's, you know capital N, you know how to calculate x bar. So then you fix this likelihood function, and then you have a function. And if you choose a different set of data, you will have a different set of likelihood functions. And that's just plot the likelihood functions with different n but fixed tau, so that you sort of see how does it look like. Okay, for this 1 over tau to the power n and exponential minus n divided by tau. We know when tau is large, this 1 over n will be small, and to the power n will make it even smaller. And when tau is large, this goes to 0, and so this factor doesn't matter. But on the other hand, when tau is small, you got exponential 1 over minus tau, which is extremely small, exponentially small, and suppressing the divergent part here. So you sort of know for tau large, okay, the 1 over tau to the power n will dominate, and the likelihood function is small. For tau small, the exponential minus 1 over tau will dominate. And it is still a small value. And since it's small at small tau and large tau, so you sort of see that there gotta be some maximum in between, right? So, nice guess. These are the likelihood functions that you got from random sampling. So suppose now you take a random sample of n equal to 5, and so then you will have different x1, x2, x3, x4, and x5, right? So plot it out. Let's count it as 1, 2, 3, 4, 5. You get these 5 numbers. And with the x1 to x5, then you can plot the likelihood functions. And you see here, this is exponentially small. Here, this is 1 over tau to the power 5, also small, power law small. And so if you plot it out, aha, there is a maximum point, tau hat here, okay? And with the same tau, if you now just randomly generate 10 signals, just 10 intervals, x1 to x10, I'm not going to count the 10 for you. So if you plot this 10 here, it has a distribution like this. And if you plot out the likelihood functions, you notice that they have similar shape, but halfway it becomes sharper. Okay, so that n equal to 10, you can extend this to n equal to 20 with more data, and n equal to 50 with even more data, and then this likelihood function becomes sharper and sharper. So what does this mean? We just assume that we have drawn the data randomly from the exponential function, right? And it has one single parameter, tau, and we don't know what tau is. So we want to make an educated guess about what the tau is from the data points. So how can you do that? And this maximum likelihood function is really the key. That is, we use this data point assuming a hypothesis and then seeing what kinds of exponential distribution will give you the most likely data, like the one that you have at hand. So we just take the maximum function of the likelihood function, and so that will give you an estimate of that. From this, you see that this tau hat is actually quite close to 4. With just n equal to 5 data, this is surprisingly good. For n equal to 2, this tau hat move even closer to 4. For n equal to 20 and n equal to 50, it is literally just on top of the true answer, tau equal to 4. And so that's just try to calculate a little bit to see how this goes, okay? So let us just find the maximum likelihood estimation for tau hat. Remember, tau hat is the argument of where the likelihood functions L tau reach its maximum. And in this particular case, because L is a single value function of tau, so dL d tau equal to 0. And because log is a monotonically increasing function, it's often convenient to maximize the log likelihood function instead of maximizing the likelihood functions. And it's a very simple exercise because log is a monotonic increasing function. The dL d tau equal to 0 and d log L d tau equal to 0 will give you the same maximum values. Okay, so just go back and take the derivative, and then you will find out what that means. So later on, we are going to use this log likelihood function. Wow, log likelihood function looks very machine learning and it looks very advanced. But remember, this is really simple. What this do is that go back to the original one. You take a hypothesis. That means that you assume a specific probability distribution function with unknown parameters, and you just plug in all the data you have. So then you got a function of L. And so then how can you determine the unknown parameter? Well, taking its maximum value, and that's it. So it's really simple. So here again, if we take the log of the likelihood functions, and this is our likelihood function, right? So then taking log of this, that's minus n log tau. So you got a log tau term. And for this, it's exponential, log exponential cancel out. You get minus summation I xi divided by tau. But summation over xi is just n x bar. So putting out the factor of n and putting out minus sign, you get log tau plus x bar divided by tau. So this log likelihood function, even though harder to pronounce, is actually easier to compute, right? You don't have this power law, you don't have this exponential anymore. And this is typical. If you think about that, the likelihood function is the joint probability density function of a direct product of n independent things. It will simplify the algebra and it doesn't affect the answer. Wow, it sounds like some commercials that I'm saying. Anyway, it's relatively simple, right? So now the log likelihood function is simple. It's just minus n times log tau plus x bar divided by tau. And you want to find the maximum value of it. Well, just take a partial derivative. Log tau give you 1 over tau. This 1 over tau give you minus 1 over tau squared equals 0. And it's straightforward that you just got that is tau hat equal to x bar. And x bar is nothing but the sum over this xi's divided by n. So nice. And in fact, as we have shown in previous lecture, that x bar is an unbiased minimum variance estimator. So how good can it be? With such a simple calculations, we already got tau hat. And this tau hat is a minimum variance. It's unbiased. It's a consistent estimate of the original tau. So that's it. So you see that the key, the success that we have achieved, in fact, is twofold. It contains two key ingredients. The first of all, of course, is this intuitive yet powerful of ML estimations. And the second thing is this ingenious observation that we start with the exponential distributions. Okay, so why do we assume that the signal transmission in a while can be described by exponential distributions? Why? And I'm going to share you that something you rarely find in the textbook, which is really important. And in neuroscience, this is called spike trend statistics. And in computer science, this is called signal transmission statistics. And they are all the same. In fact, in nuclear physics, this is called decaying event statistics. They all have similar features. That is, some things without a brain is doing some random stuff and decaying, sending out signals, or firing. Okay, it's not like very smart guys or some smart brains doing something. No, it's just a dumb neuron, or it's just some signal transmitters, or it can be some unstable elements. It's trying to decay. So I'm going to show you that there is a Poisson distribution behind this as a discrete version, and there's an exponential distribution behind this as a measure of the interspike interval. So let me redefine the spike trend statistics in the following time. In the time direction, if I mark the spiking time t1, t2 to tn and arrange them so that it's in this, I'm sorry, this should be capital N. Okay, so the t1 is less than t2, t2 less than t3, and tn less than t. So they are sorted out this way. Given a constant firing rate, what is the probability density functions of p t1 to tn? That is the question that we like to ask. And I have questions dropping in. So let's see what's the questions. Yes. Do different PDF hypotheses share the same likelihood function? this is really, really great. You have made my days. This is the $1 million question. So what do you think? The answer is no. The answer is no. So if you make a dumb guess about, well, you just make another good hypothesis about the original problems, with the ML estimation, you get a pretty lousy answer. So that's, remember one important thing, maximum likelihood estimation relies on an educated guess about what kind of hypothesis you put forth at the very beginning. If you didn't, that's why I'm explaining the spike trend statistics and try to at least give you some hint that why this exponential distribution is the right answer to guess. Okay? So great questions, excellent. If you have more questions, let me know, because I have dual screens. I can look at the questions and then move on. Okay, so in fact, this spike trend statistics has an official name called homogeneous Poisson process. And it's called Poisson process because it contains a Poisson distributions behind this. And it's homogeneous, it means it's homogeneous in time. That is, the firing rate R is constant in time. And this is just assumptions. In many scientific and engineering process, we will deal with inhomogeneous Poisson process. And if you are interested, you can just look it up. And there's a very complete literature on explaining the Poisson process, be homogeneous or inhomogeneous. So here I'm going to take some really interesting thing. I'm going to cut this time axis, the whole duration, capital T, into m bins. As I shown here, this took me quite some time to plot. And if you look at it carefully, you will find they are not equally distanced. I'm sorry about that. These are handmade. So I'm cooking out m bins, and this m is huge. Basically, it's infinity. So then, if you then just look at the time intervals, the unit of this little bins is dt. That is infinitesimal. So that is the t divided by m. So at the end of the day, you can assume that m is just an infinite number and this dt is infinitesimal. And so then, because this dt is so small, so you can assume that this bins, this temporal bins is so small. So within each bins, there at most, most of the time there's no firing event, and there's at most one firing event. And once the bin is that small, you will then mark this bin this way. If there is one firing event, you mark it in red and then call it T1 and T2 and T3 and T4 and Tn and so on. And for the others, the empty one, there's no firing events. So then, what is the probability that you observe a bin is on? Well, that's simple, right? That's just the firing rate times dt. So that's the gamma, that's r times dt. And since dt is small, so this bin, the probability for the bin is on is infinitesimal. Where the bin is off, this is almost 1, but not 1, okay? Remember that these two add up to 1. If you approximate here as 1, then you basically approximate this 0. Then you have a trivial problem. That is just a homogeneous dead process. Nothing happens there. So be careful that this is r times dt, and this is 1 minus r times dt. So then let's just look at what's the probability for this particular pattern I draw here. For the first two bins, there's no firing event, right? So the probability is 1 minus r times dt, 1 minus r times dt, and the third one is t1, that's r times dt, and then 1 minus r times dt, and so on and so forth. And in fact, according to these figures, there's only one r minus dt. There's no dot 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 here. I'm plotting too much here. And so you can repeat this pattern to Tn, and after Tn there's a 3 non-firing bins, and so there's 1 minus r dt, 1 minus r dt, 1 minus r dt. It's really simple, and because all these are independent, and so you just write it down. And so this is our probability. The next thing is that you want to simplify this a little bit. Well, notice that is 1 minus RT dt, because this dt is small. So that's just the same thing as you learn the rotation in quantum mechanics. We can intentionally write it an exponential form. If you don't like, you can multiply them together and taking the limit, you still get the exponential form. So I'm just giving you these boring limit taking the process. So I'm taking the exponential. And so then you know that how does this turn into, because then this is exponential minus r dt, and the second one is also exponential of r dt, and you add up all these things, you multiply them together, is the same as summing up all the exponent, and so then this give you exponential minus integration 0 to dt r dt, and of course r is a constant, you can put it out here, but in general if r is not a constant then you can actually stick it in. And so this is the first firing event. And then there are lots of things not firing between T1 and T2, and you got exponential minus T1, T2, and then RDT, and it just keep doing this. Then you notice a very beautiful and nice thing. So when this n base goes to infinity, you don't really care about the ends where you're printing two strings and counting the number of the bins. These factors can be combined together, just give you an exponential factor minus integration from 0 to capital T r dt. And you have n firing events, so it's just r dt to the power n. And resorting everything together, this integration is trivial because r is constant, and this integrate to t, so then you get an exponential suppression, you get a r to the power n, you get dt to the power n. This is really great because we know that this t should form a continuous random variables. So the probability should be proportional to dt1, dt2 to dtn, which is basically the volume element in that temporal space is just dt to the power n. So from the previous understanding, we know the PDF of the Poisson process, homogeneous Poisson process, is just a firing rate r to the power n exponential minus r times t. This is really cute. Okay, so starting from here, we can then derive the following thing. So the first thing, let's look at the Poisson distribution. So what is Poisson distribution? Poisson distribution means that because now I know how this arrange with probability n, right? So I can then ask this question. Suppose I don't care, I am just interested in how many firing events I can find within the time t. So then you just integrate over all possible t1 to tn. But be slightly more careful when writing down these multiple time integrals, because t1, t2 to tn are arranged, right? So when you write down the integration, this t1 is going from 0 to t2, so then ensuring the t1 is always smaller than t2. And same thing, the t2 is integration from 0 to t3, and tn is the only variable going from 0 to t. Okay, and this is the Rn, exponential minus Rt, but since this is just a constant, you just pull it up, and you need to carry out this multiple integration. That is relatively simple, because it's just a cube in an n-dimensional space cutting in n factorial times. Remember that this particular t1 to tn is just 1 over n factorial possibilities. So try it out. If you don't trust me, go to 3 dimensions and calculating the dt1, dt2, and dt3, and if you just calculating it, you will get 1 over 3 factorial, and that can be generalized to n dimensional. And so then you get a 1 over n factorial and a cube. Okay, it's 0 to t, 0 to t, so it's t to the power n. So this complicated looking limit region turns out to be t to the power n divided by n factorials. Combining the gain r and t together, you found that this is rt to the power n exponential rt divided by n factorial. Look up the previous notes that we discussed in probability distributions. You would then find that this is the Poisson distribution. So that's really, really nice. When we are talking about this homogeneous Poisson process, you can calculate what is the probability, what is the PDF, probability density functions for specific patterns, firing patterns. For T1, T2, Tn, that is r to the n exponential minus r to the t. And in fact, from here, if you don't care about this temporal distribution of the firing event, you only care about how many firing events that you got a Poisson distribution. Isn't it nice? And you can sort of view this. Sometimes we're interested in how the T1, T2s distribute over the temporal domains. But sometimes, think about this. This can be proton decay events, so then there are some contaminated emitted particle coming out. You only care about that how many particles comes out at the end. It turns out for this decaying process without master brains, without some interactors behind it, you always get a Poisson distribution. So that's nice. And let's look at more challenging questions. Okay, so now you have the T1, T2, and Tn. Suppose I'm interested in some other things. Suppose I have a detector and I just detect, aha, I catch some firing events. So what would be the next event? And you know that sometimes you need to wait longer, sometimes you need to wait shorter. So what is that distribution? And of course, that distribution is going to be continuous, right? So for instance, with this T1, T2, T3 to Tn, you can actually come up with these interspike intervals x1, x2 to xn minus 1. And if n is big, so you probably don't care about this n minus 1 anyway. And so these xi's are random variables. So what is the corresponding PDF for this interspike intervals? Well, that's actually not very difficult. So suppose now that after firing event T1, I'm interested, what is the probability that how long should I wait until that I see the next event? Well, that is that you waited for some times, right? That 1 over r, 1 over r dt, 1 over r dt, and boom, the next ones, right? And so then this T2 minus T1 is just the x1 by definition. And so then you know that the probability is this exponential integration from T1 to T2 r dt times r times dt's. Okay, sorting out the notations. So this probability of x1 is just this integration T1 D2. Remember the definition that is x1 is the interspike duration. That's just T2 minus T1. So you get an exponential minus r x1. And you also get rdt, this next firing event. But remember one important thing, that dt is just dx1. The dx1 is just the waiting time. So then it's changed. It's just the same as time. So the probability look like this, and this dt is at dx1. This is the probability, and thus the corresponding PDF is just removing this part. And so then you got r, you get exponential minus rx. And you can check. If you integrate over dx, this will just give you 1. Okay. And change simple variables, writing tau as 1 over r or r as 1 over tau, then you got this exponential distribution. So what does this mean? That means when you have a sequences like this, and if there's no other particular intervention, that all the spikes just happens with a specific firing rate. That is, firing rate is the only key element in this spike sequences. Okay, no other correlations. That is for the spike trend statistics. Then you got two similarly unrelated distribution out of this. Waiting for a time t, you can get a dimensionless number that is r times t. So r times t would be the average event that you will observe during the duration, right? And from that r times t, you can cook up a Poisson distribution. Remember, Poisson distribution is a discrete distribution. Do not be confused, okay? And so then for this spike trend statistics, if you care about how many events within a given time, you get a Poisson distribution. On the other hand, if when you got the first spike and you are curious about what would be the next spike, then you get an exponential distributions. And that's why that at the very beginning, since we look at the data and we think that this looks very similar to the spike trend statistics, so we are going to take the hypothesis of exponential distribution, and you just hit the jackpot because you make a very clever and educated guess. So here I would like to say that the maximum likelihood estimation is intuitive and powerful, but don't forget, you need to be educated enough so that you will make an appropriate educated guess about the hypothesis for the data you are given with. Okay? So how do we know that we have the right hypothesis distribution? The answer is we don't know, and that's why the science and sometimes engineering is interesting, because you only got the data, and sometimes the data is so dense and you have a huge amount of them and it's very easy to guess, but sometimes it's not. And so then it's really up to you. And think about this beautiful example here. Suppose I just give you 5 firing events. The one here is like 0.1 something, this is 1 point something, this is like 3 point something, 8 point something, and then like 12 point something. I give you like these 5 numbers and I ask, what's the probability distribution behind this? Are you kidding me? This is mathematically impossible, right? A probability distribution function is a vector of infinite dimension. With just given 5 points, how am I going to know? So there are literally infinite answers to this. Yes. So you can just wave your hand and saying, sorry, I don't know the answer. But if you know that you're dealing with, for instance, the switching board of telephone call, or you're dealing with the signal transmission in a while, or you are doing the statistics of a spiking neurons, or you are observing the decaying event of an unstable element, then the underlying probability density function is most likely to be Poisson with corrections. And that's just forget about the correction and assuming the Poisson is good enough. And once you take that hypothesis, you can actually get the optimized probability distribution functions, which is likely to generate the data that you observe. Just 5 points, and you can actually see here, this is actually not so bad. If you think about this, the CP value of this is huge. Yes, you didn't really get this tau equal to 4 right, but then you get it like tau equal to 5, but so what? With just 5 data points, this is really good enough, right? And think about this, once you collected like n equal to 50, this MLE give you almost the exact answer of the underlying exponential distribution. So the idea is that typically when you have some intuitive understanding about the statistical problems, then you employ this ML estimation and you will find it extremely powerful. Okay, so this is not like just free and for dummies. Okay, good questions. So that said, I hope that you have learned 2 things, okay? The first thing is that why we starting from the exponentials at the very beginning, it has a very deep and fundamental reason at the microscopic origin. That is, this system is generated by a homogeneous firing rate in temporal directions. And once you do that, this maximum likelihood functions is really, really simple. And so that sounds very dreamy. So then we need a wake-up call. I need to warn you that it might give you some really biased estimations. So let's go back to our actually a very good old friend, that's the Gaussian noise. Suppose now you have a Gaussian noise of zero mean but unknown variance. Okay? So basically you know there is some underlying probability distribution function. Its mean is zero, but then the variance is unknown. And it generates a set of xi. So can we use this ML estimation to find mu hat and sigma hat square, sigma square hat? And the answer is yes, we can. Okay, so how do we do that? First of all, just write down, because we assume it's Gaussian, right? So you just write down its probability distribution function with just mu and sigma square. Remember that these are functional form. So this is a functional dependence. So these are variables. They are not particular value of mu and sigma square. Okay. So then we just write down these joint probability function with this xi. So you plug it in, then each one is a Gaussian distribution with two parameter mu and sigma square. So then you got this likelihood functions. Taking the log of likelihood functions usually simplify the algebra, and you can see it is indeed so. So taking the log of this is 1 over square root, give you minus 1/2, and then log 2 pi square square. And here log cancel this exponential, and then you got minus 1/2, the same factor, and xi minus mu squared divided by sigma squared. So you just got a very simple functions like this. Okay. And I'm going to trading what some people using sigma as variables. I has tendency to trading sigma square, the variance, as the variables. So bear with me. So I'm taking sigma square as something. Okay, so this is a log linear function. And so if you take d log L d mu, and this term doesn't depend on mu, and this taking it, you bring down 2, and these are all bunch of constant because equal to 0 doesn't matter. So then you got this summation I equal to n xi minus mu divided by sigma squared equal to 0. That's the first equation. The second equation is this likelihood function divided by sigma squared, and then taking the partial derivative to sigma squared. I'm writing sigma squared as some function like z. Okay, so this would be like log 2 pi z. And log 2 pi is a constant, drop out, so log sigma squared, taking partial derivative with respect to sigma squared, give you 1 over sigma squared. This is 1 over sigma squared is 1 over z. Taking partial derivative of that, you get to minus 1 over z squared, that means 1 over sigma 4 squared, and xy minus mu squared, that's the same, and equal to 0. So then you got two equations. You can find mu hat and sigma square hat. Mu hat is trivial. Looking at the first one, you can directly solve it because this is non-zero. And so then you got mu hat is just our ordinary friend. So now you should know. So this MLE is for the Gaussian distribution. Just give you this really nice automated estimation of mu hat, which is x bar. That is the average, the sample average of the data. But what about the second equation? Okay. Once you know that you get into the second equation, you multiply this whole thing by sigma to the power 4. You get sigma squared minus xi minus mu squared. But remember that mu take on, this mu here is not really the true mu, right? It's take on this, you need to solve these two equations together. So this mu take on the x bar. So in fact that you solve this sigma square hat is 1 over n summation I from 1 to n xi minus x bar square. This is a little bit unfortunate. Why? This sigma square here is not really the unbiased, the sample variance. For MLEs, it doesn't give a bias estimator. For mu hat equal to x bar, it's unbiased, it's minimum variance, it's good. It's good. But for sigma square, because you got 1 over n, you can put in the n minus 1 and then multiply this by n minus 1 divided by n. So then from MLE, you get sigma squared hat, which is not S squared. So that means it's bias. If you don't trust me, calculate the bias. The bias is the expectation value of this minus sigma squared, and this is n minus 1n expectation value of square, which is sigma squared. So subtract that, you then got minus 1 over n sigma squared, which is not 0 for any finite n. So it's a little bit unfortunate, and even for very simple Gaussian distributions, these MLEs simultaneously give you this mu hat and sigma square hat. It's powerful, but it's not quite correct. Okay, so try to keep this in mind. There is no a priori or there is no fundamental principle enforcing that this ML estimation will just give you unbiased estimators. So sometimes from this maximum likelihood functions, you will get a biased estimators. But in fact, you can show that in the larger n limit, it will be consistent. So it's not perfect, but it's intuitive and it's powerful. So use it with care. Once you know how to cook up the right hypothesis, once you know that sometimes it will give you the bias estimator, and once you know that its efficiency might not be optimized, but as the sample size grows, you will find MLE estimators always shrink with 1 over square root n, governed by the central limit theorem. Then overall, you will find why the maximum likelihood estimation is such a powerful and popular tool in statistics. And because this is the tool that we can learn from the data, nowadays MLE has become one of the very powerful theoretical backgrounds for machine learning. Okay, so that would be all that I would like to say, and I do hope that you sort of pick up this relatively simple yet powerful tool for maximum likelihood estimation. And I do hope that you won't be as puzzled as these magpies varies by a huge amount of data points. Okay. Okie dokie. So that would be all that I would like to share with you today. And I hope that you sort of find these videos fun. And if you have any questions after our YouTube live, you can leave your comments below. And if I see it, I will reply to your inquiries. So that will be all for today. See you next time.